Hi, in this lecture, we're going to finish up the neurophysiology by looking at how the action potential is propagated through the axon. So remember that the action potential starts up in the axon hillock, and then it has to travel all the way down the axon, because remember, they follow the all or none law. So if we look at this image here, once we start, it needs to go all the way down to the whole length of the axon, all the way down to the telodendria and those axon terminals. So how do they do that? Well, there's two ways that this happens. It is either called continuous propagation. Continuous propagation happens in unmyelinated axons. So we might call these gray fibers. Remember, fiber is axon, and it's going to be much slower than saltatory propagation, which is going to happen in the myelinated axon. So if we come to this image, you'll see the saltatory and the continuous. So continuous and unmyelinated, each segment has to depolarize. So sodium comes in and it depolarizes and potassium leaves, and it just kind of propagates all the way down. Each piece of the axon gets depolarized. Saltatory, however, is more like a leapfrog or a jumping. Saltar is the Spanish verb for jump, and so the impulse here kind of jumps from node to node. Remember, the node was the gap between the cells. These are Schwann cells here, and so it jumps from node to node, which means it's able to travel faster. So it basically, because you have the Schwann cell insulating, it kind of goes around the Schwann cell, and then that piece depolarizes, and around, and then that part. So it only has to depolarize the nodes, which makes it move a lot faster. So this is a little animation in YouTube that I found that might help you visualize this. So take a second to see the anatomy of the neuron. Notice we have our axons. The top one is unmyelinated, and the bottom one has the Schwann cells, and it has the nodes. So let's see what happens when we shoot that nerve impulse down. Do you notice how it's jumping past the nodes, whereas continuous has to depolarize each piece of it? So this might be helpful to see how it leapfrogs, which will make it travel much faster, versus having to depolarize every single piece of that axon, one segment at a time. So the myelination increases the speed of nerve impulse conduction. Another thing that affects it is the axon diameter. So we know that we have this flow of ions, right? We're depolarizing, they're moving, and we know that if you have a larger diameter, you have less resistance. So what that means is that the action potential will travel faster in a larger diameter axon than a smaller. Now there's several ways of classifying these diameters, these fibers. So we're keeping it simple. I'm keeping it simple and just saying type A, B, and C. Understand that the type A have several subtypes. Okay, we're not going through all of those. But what you see in this image is clearly, and we'll go to the simple one first, an A, a B, and a C. And on first glance, you should see that the type A have the big diameter and the type C have the smaller. Now, if we come over to this image, notice the type C versus your different A's, and this would be your B. Notice that the C fiber does not have myelin on it. So it's unmyelinated, whereas the A has a really, really thick amount of myelin, and the B has an intermediate amount of myelin. So in this image here, the better view would actually be to just show it as just the axon, just to show the nerve fiber without the myelin on it. So C are unmyelinated. That's not really a very pretty picture, but you get the idea. All right, so let's look at these. So our type A are heavily myelinated. They're the thickest myelinated, most myelin, biggest diameter, fastest. So they send information about 250 miles per hour. That's pretty fast, right? More than enough to get information from your big toe to your brain. So they carry rapid information, such as somatic motor. So they control our skeletal muscles, especially for reflexes, right? And balance and posture. They bring information in regarding touch, especially anything having to do with cold or what's called fast pain. So fast pain is that sudden onset of pain, like you stub your toe, right? You step on something sharp, when you get a needle stick. That's fast pain, and these are all type A fibers, so they're going to get that information to your brain really fast. Now our type B are the intermediate. So they have some myelin, not as much as the A. They have a medium diameter. They're smaller than the A, but bigger than the C. So they're a medium speed, about 32 miles per hour. Now you don't have to memorize the miles per hour. I'm just showing you how fast these things are. So even though this is slower than an A, 32 is still pretty quick. These mainly carry information for our autonomic nervous system. Remember, taking information to our cardiac muscle or to our smooth muscle of our digestive organs. And then the smallest ones are the type C, and these are the unmyelinated. So they're very small, they're unmyelinated, and they're very slow. So they transmit about 2 miles per hour, which still is not bad, right? So they carry slower information. So they transmit slow pain, which might be like a chronic pain that you feel. They carry information about temperature regarding more like warm. And they also can transmit touch and even your sensation of itch. So you might wonder, why have 3 different types of fibers, right? Why not just make them all these type A fibers and make them all super fast? Well, the reason has to do with space. You know, you have so many nerves and you can only have so big of a spinal cord for all this information. And so I read once that if all of our fibers were type A nerve fibers, so all the axons are type A, then each nerve in our body would be about the size of a typical garden hose, which would mean that our spinal cord would have to be the size of one of those big trash cans. And obviously that's not very flexible or very mobile for us. So we sacrifice speed so we can have smaller size nerves and we can be a little more compact. So I told you this was a quick one. That's the end of our lecture on the propagation of the action potential.